Hello everyone, welcome to this week two's lecture of the course on control engineering. My name is Ramkrishna. I'm a faculty of electrical engineering at IIT Madras. In week one's lectures, we learned a little bit about the basics of control, starting with a motivating example of a single tank system where we had inflow of water, we had an outflow of water, and the aim was to regulate the height of the water to a certain desired level. Through that example, we defined the notion of a feedback. We also defined the notion of a feed forward, and also saw how by adjusting a certain quantity called a gain, we could achieve our target height faster. In that process, we also defined the notion of an open loop control, a simple example of a fan that we use in our day-to-day lives. We also had defined a general control architecture, in which case the standard problem of any control system is given a plant. Given a plant, the objective is to make the plant perform in a certain way. The plant could be a car, which we want to go at a desired speed. The plant could be a room where we want to regulate the temperature to a certain, say, 24 degrees and so on. In that process, the first objective was to understand what the plant looks like, the way it behaves. And we classified plants into several categories, starting with static versus dynamic. We also had classified them as linear versus nonlinear. Then we went towards time invariant systems, causal systems, and so on. In this lecture, we will look at a little more we'll expand a little bit our horizon to detail a little more of what we see in this architecture. What we see are okay. I start with a reference signal, essentially meaning. So this is my reference signal, which is a desired speed which I want to follow, a desired temperature which I want to achieve, and so on. So that I denote as R of t. Then I will have a control signal. So based on my reference and my plant, my controller will design a certain signal called U of t. Okay, this are in this will pass on a signal to the actuator, and actuator will generate the physical energy to drive the plant to the desired state. We could also have disturbances in several forms. Say I'm in a room, disturbance could be like a door open. When I'm driving a car, the disturbance signal could be in form of an uphill or a downhill and so on. Okay, so we have, and finally we have the output, which is the way, which is my actual speed or my actual temperature. In a standard feedback loop, the output is measured via a sensor, and maybe the sensor is maybe subjected to a certain noise. This output is fed back to the controller, where the controller will compare the reference versus the actual output. If they are if the reference is not equal to the actual output, the controller will compute a certain control signal, which will be passed on to the plant and so on. Okay, so what we are largely looking here is at several signals: the input signal, the output signal, the disturbance signal, and there could be several other internal signals that go on inside this loop. This is a simple loop. There could also be situations where we have loop inside a loop and so on. Okay, so this week's lecture we will start by looking at various signals that we could encounter. Signals also in the form of how does given a certain input signal, how does the output signal look like? What are the different ways of output? A simple control problem to formulate would be given a plant and there is a certain reference signal. I start with a certain reference signal. I call it R of t. This R of t goes through a controller. The controller generates the input to the plant, and the plant generates the output Y of t. Okay, so what is the objective? Objective is to make y of t equal to r of t. That the output must strike the reference. That my car must go to the speed which I set in advance, say 60 kilometers per hour or 100 kilometers per hour. Okay, now look at the input-output relations. If I can just say the output y is caused because of the input u going through the plant p. Okay, now this is the input-output relation for the plant. Similarly, I have this controller C, which takes R as input. So I'll write it as R of t times C will give me U. Okay, now I have Y is P times C R of t. Okay, so in a very loose sense, if I say Y will be equal to R if P times C is just 1. Or in other words, C can just be the inverse of the plant, right? So C can just be the P inverse. Or one thing to say, how would I make my plant achieve a desired reference signal? I'll just say, choose the controller, which is just the inverse of the plant. Okay, what else could happen? Well, what else could happen is, well, maybe my plant is subject to certain disturbance signals of what I see here. Okay, so there could be some disturbances to my plant. In that case, what do I do? What I still want is y of t is equal to r of t. Okay, now where does this y come from? This y comes from p times the signal coming from u, which this controller gives me, and the d, and so on. Okay, I still do the same math. So here the output y is y, input ut is this one. D is a disturbance, could also could be in whatever form, but in standard we'll just for this we will model it this way, and p is the plant model. So y equal to rt can be achieved simply by looking at the solution u equal to p inverse r minus pd. Okay, I'll just as a quick exercise, verify this. Okay, and this P inverse is also referred to as the model inversion. Okay, if this was the entire control loop, I don't even need to look at feedback, because all I need to do is to do a P inverse. If there are disturbances, I can still handle. Is this all? If it is as simple, we could just end the control lecture here and have just a 1 week course. But things might be and might not be as easy as they seem here. For example, one needs to describe the plant exactly. Okay, so even the mass, say the plant will consist of all the physical properties of the system. If you had a circuit, it would have the R, Ls, and the Cs, the gears. A pendulum should have the mass, the length, everything should be accurately measured. And if I could measure that accurately, only then I could invert it accurately. This also needs to be well posed, right? So, and also we also need to look at things like stability, and that P inverse actually exists by definition. Disturbance also needs to be known to be the disturbance that we measure here, the D. We also need to know that exactly to compute the U, right? Because the formula for the U directly depends on disturbance. I can say, okay, I have a really sophisticated method of computing the plant, but what about disturbance? It doesn't come with an advance notice. Okay, and of course, the signal U needs to be realizable. One must not violate any constraints. It should not tell that, oh, that my car should pump in or my motor should produce a certain torque which might be beyond the physical limits, and so on. But nevertheless, this is the first situation that we will look at, how to track the reference. First is, okay, invert the plant. And we conclude that it is actually not that simple. Okay, so second thing is what really happens? How does the system input output behavior look like? I'll not do the details of this, but we'll just see what are the possible scenarios that could happen. Okay, So let's say I have a reference signal. I mean, I start my car and I say I want to go at a reference. Let's say this is 60, say some speed normalized to 1. Okay. And this starts at, say, sometime here, which is the plant output will also show up. One thing that we definitely know is that the system will not go to its set value immediately. Now, just as I switch on the fan, it doesn't go to its desired speed immediately. It goes a little slowly and then it kind of settles down to this. Okay, so the input and output. So what we see here is there are certain, and I think we also call this as the system transients in week one's lecture. Okay, so I have a reference, the output writes the reference, but what I see here is there is some time between the time I switch it on and the time it reaches the desired value. What I also see is something not very nice here, right? I want to go to 60, but I actually instead my speed goes from, say, this is zero speed, this is say 60, speed starts from 0, maybe goes to 65 and then comes back to 60. Is that really desirable, right? So why, and this is what we will also call or define as a overshoot. Okay, in some other cases it could just happen that my system starts from 0 and slowly reaches the desired value. What will definitely not happen is the moment I switch it on that it reaches the speed 60 and then stays there. This will never happen for obvious reasons, right? So in a way that if I really want to make this happen, I would need to pump in infinite energy into the system. Okay, so just like a speed control of a car, right? So if I just look at, so my input would be my pedal position, which would generate a certain engine force, and the speed would slowly start from 0 and reach, say in this case, say 20 kilometers per hour. Okay, this is what we know and we kind of experience in everyday life. Suppose there is a disturbance in the form of, say, a step disturbance. Step disturbance could be in a way that I'm just still going at the same speed, and say all of a sudden, if there was one person in the car, now say there are 6 people in the car. That kind of adds to the mass, right? So because your relations are all F equal to ma, so the number of people increased from 1 to 5. At the same time, my fuel tank went from a low level to the maximum level. So maybe my mass has increased 4 or 5 times. So that is like, so if this was the mass, then the mass increases and it just stays here to a new value. It's called as a step disturbance. Okay, we'll also see why I call this step and what are the other form of disturbances that we would encounter. For now, we'll just assume that the step disturbance means that the mass of the car increases all of a sudden from, say, some value to some much higher value. Physics would tell us that if I'm just putting in the same amount of force to push something which is now 5 times heavier, physics would tell me that with the same force, I really cannot go at the same speed, that the speed has to come down to something. Unless I recalibrate and recalculate my force. I'm not doing that. The same force with disturbances, I see that my steady state speed now settles down. It starts from 20 and goes to 5. So, in conclusion, the output takes a new value in the presence of a disturbance. Okay, first observation. How we will deal with this? Is this really good? Is this bad? We will not worry about that. What I know now is that in presence of a disturbance, my output will not really stay at the value which I desire. Okay, now I go to a closed loop architecture. So where again I have a plant which needs to follow a certain reference. I have a controller which computes the control law, and there's an output which is measured subject to measurement noise. Here is my sensor output. Okay, and then there is something. So now there's a reference which will compute the output y or maybe y prime, which is a little noisy, and see if there is an error. Error in the sense that if my reference is say 60 kilometers per hour, output is say 40, then my error is R minus Y is 20. There will be some error, right? So like if I look at this problem or this situation here, this uh, so this was my actual value. But you see, I don't really go from time equal t equal to 0 till here. I will have some error. The system output is slightly deviating from the reference signal. So I'll have an error signal. And one good thing also, which will kind of provide us with nice tools to analyze, is also the error signal. So I have the reference. I have sorry. So I have the reference signal, I have the input signal, the output, the disturbance, the noise, and all these signals. Maybe I can call this as V of t, the output of the sensor. And all these are all signals, and they represent nicely how information flows in the system. And all the signal flow will be essential for our analysis and control purposes throughout this course. Okay, how do these signals internally look like? Okay, I just take a standard closed loop architecture where at t equal to 1, I set my reference to be 1. Okay, my reference is 1. The controller will, based on, and at t equal to 0, my output starts with 0. So t equal to 1, right? So this is time t equal to 1. Is when I say, hey, go from 0 kilometers an hour to 60 kilometers an hour. Okay, what is the speed? Or it could be temperature or any physical quantity. It could be even current, voltages, and so on. What is the speed at t equal to just 1 plus? So just when I switch on the air conditioner, the temperature just after I switch on the air conditioner, it's just the same thing, right? So it will start with a 0. The desired is 1, and therefore I will see that the error here immediately jumps to 1 as soon as I switch on, right? I want the temperature to be a certain value, or the speed to go from 0 to 1. Instantaneously, that doesn't happen. So as soon as I switch it on, my error is 1. Okay, then the controller will compute a control law which will drive my system to the desired levels. Okay, so eventually the output will, the controller will send a control signal, with the signal which will go to the plant, and part will generate an output which will eventually go to a desired value of 1, and the error will also go to 0. Okay, so different things to analyze here. The error signal, I have the reference signal, I have the measured output, and also I can see how the control input. And once I reach the desired temperature, my control action, well, if I were just to hold it at 1, the control action also stabilizes to certain value of, say, u equal to 1. Just say if I were to hold this pen in the nice upright position. It may not happen here, but may want to have to do some manipulation to just hold it at this point, or pump in some control energy to hold it at that point. So u will be equal, you will take some value and it will just stay there. Okay, so even in the closed loop, what is the effect of disturbance? Okay, so I'll do the same thing. So I start again with in a closed loop. In this case, you see that the signal has some kind of a noise. It's like kind of a wavering signal. So I start again with the same thing. I need to track a reference speed of 20. At t equal to 200, I see a disturbance here. Disturbance changes the value of the output to, and then because of the closed loop thing, so we'll just compare with what is happening with the open loop. In the open loop system, I had a disturbance and the output took a new value in the presence of this disturbance. What will happen in a closed loop, or what could happen, or we could design a controller in such a way that the effect of the disturbance can be negated, right? So you see here, right? So I start off with this nice looking curve where it settles down to 20. Say at t equal to 200, something happens, a disturbance happens, like my mass increases 5 times and so on. The system would not immediately respond, just like it doesn't immediately go from 0 to 20. It will take some time, right? So the system will now there will be some output, and there will be some error now between so this will be 20, this will be 20 when there is a zero error. When there is disturbance, the output might change to some new value. That new value will be fed back, resulting in some error. You see, at t equal to 200, I have a new error here. Okay, this error will be fed back. The controller will compute a new control law, and eventually I see that my disturbance or my system settles down to its original reference value, even in the presence of disturbance. So the feedback control loop has the nice effect of negating the effect of disturbances. Again, throughout the course, we will see how to actually design this. So this is just an introduction of what kind of behavior we could expect. Okay, why is it always that my system goes to the desired value? It may happen that, say, I set my temperature to 24, but the way my system designed is it may just go to, say, 24.3, giving a error of zero point 0.3 in the steady state. Maybe I set my fan to go at, say, 200 RPM. Maybe it just goes to 198. These things could also happen, right? So in an architecture like this, it could be possible that even though my reference is 1, the actual is just zero point 0.9, resulting in an error or a steady state error of 0.1. Same thing, even the moment I switch my controller on, the plant output will still be 0. So I start with an error of 1, and then my steady state error, after all the transients have died down, this is all the transients. After all the transients died down, because my reference is 1, actual is 0.9, this reflects nicely in the error signal being of a value of 0.1. Okay, so this phenomena is called tracking errors. We'll also see, are there any ways to minimize these errors or completely eliminate these errors? Okay, now suppose we have talked about the example of an inverted pendulum, right? So if I say talk of this pen as an inverted pendulum, I perturb it slightly, it'll again come back to its rest position depending on the nature of damping. Suppose I invert it, right, and try to hold it at this point, right, and it'll always fall down, right? So I start from here, it just goes down. Or of course I can do some jugglery to try to just put it in this upright position. Of course, that also is requires some kind of balancing act, that you feedback, you push, you can everybody were done to do. You can try to balance a big stick on your hand and so on. What you do is you kind of try to do a feedback and try to stabilize it. What happens if in an open loop situation, I start from here, the little perturbation, and the pendulum just kind of falls off. So the situation where it just falls off is what we will call as an unstable behavior, where the output goes unbounded mathematically, right? Where it just the system moves away from the position that we want it to see it. Like in the pendulum, I just want it to be in the downward position, and in the inverted pendulum, I just want it to be stable like this. Okay, so what could happen? Okay, I just start with a reference and an output. It could happen in case of an open loop system that the system goes unstable, like in the case of the inverted pendulum. Uh, System goes unstable, but it is possible that with just some kind of feedback effect, I can stabilize the system. So feedback will also have a stabilizing effect on systems which are by themselves open loop unstable. We have not yet quantified what is the definition of stability, but for now, this little example should be okay to visualize where we are heading in this argument. Okay, so this was all about signals. We had the input signal, the output signal, disturbances, error signals, the output corrupted with some noise, and so on and so forth. So what is a signal? A signal is a function that conveys information about the behavior or characteristics of some phenomena, like the progression of temperature during the day, or an ECG signal, and so on. So typically, if I look at a signal, it is typically represented as a function of more or one or more independent variables like space or time. Time could be like the temperature during the day. Space could be of I start from Chennai, go to Bangalore. Which part of the traffic is more dense? Which part of the traffic is less dense? That is largely a space-based signal. Which part of the traffic or the road has more pollution or less pollution, right? So these are largely examples of signals. If I look at just circuits, I can talk about voltages or currents, sound waves, and so on. Noise is also a signal, but in general the information is like unwanted, and we will not really analyze that much. We'll see how we can possibly mitigate the effect of noise. And in general, it's an undesirable phenomena when we talk in terms of systems. Um, Slight classifications, of course, we will still not go much into the details of this. As I said, we will largely look at linear time invariant system signals, and largely in the continuous domain, but not in the discrete domain. However, it's nice to just recall what we had done in our signals course. We have analog signals, these signals that have continuous variation over time and are represented using smooth, uninterrupted waveforms. These are analog signals. Digital signals whose amplitude can take only maybe like a finite amount. Sorry, any finite number of values. Uh, Next, we can have a signal that is either continuous with time or discrete in time. So typical examples of continuous signals would be audio signals or voltages and currents and so on. Signal is said to be discrete when it is defined only at discrete instance of time, like digital audio files. I'm taking sensor readings periodically, say after every 5 minutes, or I do the population count, say once a year or once in 10 years, and so on. Pictorically, they would be represented as the picture on the left would be the discrete signal, the picture on the right would be a continuous signal. Other classifications of signals are also deterministic versus non-deterministic. Again, by definition, a signal is said to be deterministic if there is no uncertainty with respect to its value at any instant of time. For example, I can accurately say what is sine 30 degrees, or any signal of a form, say if it is e power minus t sine t, I can accurately calculate its value at any given point of time. Similarly, I can, and any signals which have exponential growth or exponential decay, as we saw in the predator-prey models, and so on. Non-deterministic signal is one whose value cannot be accurately precisely predicted, even if its past behavior is known. Right? So there'll be some randomness, there'll be some uncertainty. So there'll just be some kind of expected values. So say if I look at a cricket match, I can only predict what will be the score at the end of 20 overs, given maybe 5 overs or 7 overs data. These are all, or can only predict how well a player will perform, or even a stock market. I can only predict how good or bad a certain stock will do, right? So there is some kind of randomness, so I cannot predict the value or I cannot determine the value accurately. So examples would be any kind of white noise, stock market prices, and so on. Okay. The next classification of signals are even and odd signal. Again, this we do as early as from our school days. Even signal is one that is symmetric about the vertical axis. Yeah, mathematically, it would mean that x of minus t is simply x of t. Odd signal would be that it is kind of symmetric about the origin. Like that's the kind of the geometry of looking at it. Mathematically, it would mean that x of minus t is just the negative of x of t. Signals could be periodic and aperiodic. Periodic signal is the one that repeats its pattern over a regular time interval. It has a period which like a 24-hour cycle is or a week cycle is a periodic one, or a 24-hour day cycle is a periodic signal. And this has a fundamental period that is fixed, a t which is greater than 0. This is the smallest positive integer or the smallest possible time interval after which the signal repeats. Mathematically, I'll just say that the signal should repeat after every period t, like a sine wave. It will repeat itself after every 180 degrees or 2 pi radians, so to speak. Aperiodic signal is it does not really repeat itself after any regular intervals. It may either decay or have some kind of an unpredictable behavior. Could be any of the signals like this, or any combinations of this. Periodic signals, you can see there is a nice pattern. I have this square wave. There could be some kind of a sawtooth kind of formation, and so on. Of course, this all we know in from our earlier courses. So to summarize, what we did in so far is we classified or uh, we classify types of signals in a control loop. This could be reference signals, input signals, disturbance, output, error, some kind of noise. And we also did classifications, some very basic classifications: digital, analog, deterministic versus non-deterministic, and so on. So this kind of gives us a little more details of what should come, or where we should focus on. Right? If I look at a typical control loop, my focus should be, if I look at all these plots, that my system should be stable. If it is not open loop stable, can I make it stable via some feedback? Second thing is, if I want to achieve 24 degrees, I may not be satisfied with 24.3. I may accurately want to go to 24 degrees. Is that possible all the time? Or in which classes of systems that is possible? If it is not possible, can I make some additions in my control law that will make the error, steady state error, or the tracking error go to 0? Effect of disturbances, right? How can I smoothly handle disturbances? And largely of what are the different signals. If I also look at the things here, I switch my controller on at time t equal to t equal to 0. I would just, ideally would expect things to go to the desired value immediately. That may not be possible, right? In some cases, if I want a faster response, I might go beyond the desirable values in some sense. Say I want to drive my value of the motor speed to some desirable value, or a certain torque that I want to achieve. If I want to achieve it like really fast, will it kind of have a surge current, for example, right? So something like this. So this is what we will call as overshoots and so on. So what are these? How do we quantify each of these, and how do we design appropriate control laws? Is what will be coming up in the future lectures. And typically, so in particular, we will look at how system would respond to certain input signals. That's coming up in the next lecture. Thanks for watching.